This is lesson 19, the first of 2 lessons in which we'll cover geometry. Before we can start talking about the concepts of geometry, we need to talk about what geometry is. In fact, where does the word geometry come from? Well, if you look at the word and break it down into 2 parts, geo and metry. Metry means to measure. Geo is the earth, like geography or geology, measuring the earth. And I am told, again, I'm old but not that old, that in ancient Egypt, when the Pharaoh wanted to collect taxes from the farmers who benefited from the overflow of the Nile and enriched their earth so they can grow crops, the Pharaoh needed to be able to measure the amount of land that the farmers had so to know how much to tax them. And the Pharaoh sent his mathematicians out to measure the land that the farmers had. And they looked at the various shapes, and of course they didn't have helicopters to fly over it, but had to look at the various shapes and tried to find ways to actually find the area of each piece of land. And from this, they developed various formulas and even names for the various shapes. So that's what we'll talk about in Lesson 19 and Lesson 20. In fact, we want to first talk about why we need to know geometry. I mean, everything so far has seemed to involve arithmetic. Why geometry? Well, first of all, geometry is very, very visual. And for some of us, we need to have a visual picture before we can understand something. And that's very important. I'm like that. I'm very graphical. I like to see a picture, a graph, a chart, as opposed to someone telling me something. Also, geometry is very specific. The words have very specific meanings. And, a good example, I guess, many years ago when I first started teaching, I did a little experiment. I had 2 classes. One was a pre-calculus class, a class that already had geometry, and one was an algebra class, Algebra 1, who had not had geometry. And I divided the 2 classes up into teams, and each team got a picture, a shape that had squares and circles and other geometric shapes. One of the people in the group did not see that picture. He or she had to go to the board and draw the picture as the other members of the team explained it. And my idea was that the people who had geometry would do this much more quickly. And we had a timer. And I actually had a audio tape recorder, and we recorded what they said. And I went back and replayed it and noted the various geometric terms used. And of course, it was very interesting. Typically, the pre-calculus students did a much faster job and used much more specific geometric terms. The algebra students who had not had geometry, except for one group, took more time and did not use very specific terms, very general terms, which was confusing to the person who was trying to draw the picture. The one group, the one team of algebra students who actually were the fastest in terms of completing the picture, had one student who obviously had seen World War II fighter movies, you know, where the airplanes fighting each other, and the fighter pilots developed the notion of clock. And this young student said, draw a line from 1 o'clock to 8 o'clock, from 8 o'clock to 4 o'clock. And again, in effect, he was using geometry because he was being very specific and using a visual picture. So it was a very interesting experiment, and therefore I think it's necessary for us to have a handle on geometry to understand how to specifically describe something. And that's one of the other good purposes of geometry. Also, over the many hundreds of years of mathematics, geometry has been used to show or to explain abstract concepts. That is, concepts we cannot visualize and picture, and therefore we use geometry to try to act as models. And geometry, of course, is generally used in models and, of course, in measuring. A good example of models is a scale drawing. I mean, if you had to draw a picture of your house or apartment, the size of the apartment, it would be very, very cumbersome, very difficult to use. So they do scale drawings. And the same thing for airplanes. How do they do that? Well, the scale drawing, in effect, looks just like the house or the airplane or whatever, the room, whatever it is, but it's a smaller size. And that's something called similar figures that we'll not necessarily talk about here, but is discussed in high school geometry. Here we're just trying to get an understanding of the basic ideas, the basic names in geometry. In fact, talking about the basic names, let's look at some of the basic shapes, since geometry is about shapes. And in geometry, we talk about dimensions. So if you'll see the chart on your screen, it has a name, the number of dimensions, and what it measures. For example, a point. A point has no dimensions. Now, we draw a point, a dot, on a piece of paper or a chalkboard or a whiteboard. That really isn't a point. A point is a location. It has no depth, it has no height, it has no width. It is simply a location, 0 dimensions. A line has 1 dimension. It has length, and we use it to measure distance. That distance could be called length or height or width or depth. No matter what you're measuring a distance, and a line is used to do that. And a line, by the way, goes on forever and ever in both directions. We'll talk about what the real geometric name is for a part of a line, the kind of thing we use to measure distance, shortly. Okay, then we have 2 dimensions. 2 dimensions is the plane, and basically that's a surface. And it has length and width, and we measure the area, and we will talk about area towards the end of this lesson. And finally, we have 3 dimensions, and that's space. And of course, we live in a 3-dimensional world, okay? And each of us as human beings are 3-dimensional figures. We have height, we have width, and we have depth. And that's volume. And we'll talk about volume at the very end of this lesson. How about a 4th dimension? Well, many people would say that a 4th dimension is time, and even a 5th or a 6th dimension. We cannot imagine that, and I wouldn't even try to talk about it at this point right now, because we're really concerned about the kind of geometry you should know about. But there are many investigations mathematically going on looking into dimensions beyond the 3rd dimension. And if you're interested in something like that, I'd recommend a very good book written many, many years ago, about 100 years ago in Victorian England, called Flatlands. And it talks about a 2-dimensional world. Quite interesting. Actually, it was a political satire, but it's full of geometry. And it's something that I think a young person would understand, and an adult would probably find it very interesting, and in some cases, quite amusing, dealing with a world where everybody is a 2-dimensional rather than a 3-dimensional figure. Let's take a look at certain shapes that are made up of lines or parts of lines. First, we come to 2 parts of a line, and that is the segment and the ray. A segment or line segment is simply a piece of a line. To segment something is to break it up. A segment has an endpoint on each side. So that is exactly what we use to measure. For example, the edge of a ruler would be a line segment. And if we measured a 2-inch distance using that ruler, that 2-inch edge of the ruler would be a line segment. So a line segment, again, has specific length because it has endpoints. A ray really has no specific length. A ray goes on forever and ever. It has one endpoint, and it goes off to infinity in one direction. Now, you might say a ray is half of a line, but what is half of infinity? That's another show altogether. But either a ray has one endpoint and goes to infinity. It is a part of a line. If we take 2 rays and have them meet at their endpoints, we have an angle. In fact, that is the definition of an angle. It is 2 rays joined at their endpoints. And that place where they join, that point, is called a vertex. And a vertex is a very common word in mathematics, generally meaning a point. Something interesting is happening at that point. In this case, we have the joining of the 2 rays to form an angle. We'll talk about angles in more depth shortly. We also have a general figure, a 2-dimensional figure called a polygon. Here's an example of a polygon. Poly means many. Gon means side. So polygon has many sides. Triangles, rectangles, pentagons, octagons like stop signs are all polygons. Now, what is a polygon? Well, a polygon is a closed figure, which means if you're inside, you can't get out. If you're outside, you can't get in. All the sides are line segments. That is, there's no curvature. There's no circular parts of a polygon. All the sides are line segments. The line segments are joined at their endpoints. So there's no parts sticking out. And therefore, you have as many sides as you have that many angles. So, for example, if we have a 7-sided polygon, which I believe is called a heptagon or a septagon, depending on what you believe, you would have 7 line segments, each joined at the endpoints in a closed figure, and you'd have 7 angles inside that figure. We also can talk about circles. A circle is used to represent 360 degrees. Why? Did you ever wonder about that? I'm sure you've heard that there are 360 degrees in a circle. Did you ever wonder why? I mean, it's a magic number. Someone just fell in love with 360? Why wasn't it 100 or 1,000? You know, and of course it could be. You could have a circle measurement that it was 100 whatevers in a circle, or 1,000, or 9.6 if you like. But 360 had a very important reason, and that is that back in ancient days, and I believe it was the Babylonians, believed that there were 360 days in a year. And obviously they were close, but it wouldn't be accurate today, but for those days it was quite good. And therefore, picturing the sun going around the earth and the cycle of the year being 360 days. And notice I did say the sun going around the earth because in those days they did believe that. The cycle of the earth's year was 360 days. And it made sense that this cycle was a circle. Okay? And in fact, so much of our measurements come from that 360. In fact, the Babylonian number system was based on 60. So we have 60 seconds in a minute and 60 minutes in an hour. Do you ever wonder about that? Well, it's all based on the Babylonians' love of the idea of 60, and of course 360 is 6 times 60. If we cut that circle in half, we'd have 180 degrees, and that's a very important number, half of a circle. If we cut that half a circle in half, we have a quarter of a circle, and we have what's called a 90-degree angle, or what's called a right angle. And without right angles, we wouldn't have buildings that stood up because things would fall over. One of the most important things is building things so that they're right angles to the ground. Sometimes a right angle is called perpendicular. That is, 2 lines that meet at a right angle are perpendicular. Now, we have 2 basic types of angles that are defined by the 90-degree and the 180-degree angle. By the way, sometimes the 180-degree angle is called a straight angle. Okay. We have an acute angle, not acute angle, not the angle is cute, but acute. Acute means sharp, like an acute pain, okay? And an acute angle is between 0 degrees and 90 degrees. So a 10-degree angle or 17-degree angle, an 89.9-degree angle would be acute. 90 degrees is right, and between 90 degrees and 180 degrees is called obtuse. Obtuse means dull. If someone is being obtuse, that means you can't understand what they're talking about. They aren't being sharp. And what I like to talk to my students about is if you had to be shot with an arrowhead, would you rather have an acute arrowhead or an obtuse? And I think, assuming they're both not too sharp, the obtuse would penetrate less into my arm or chest wherever the arrow was shot because it wasn't quite as sharp. Okay, now let's take a look at this angle. We have an angle of 39 degrees. That little square in the corner of the big angle indicates it's a right angle, that the 2 line segments are perpendicular. What I'd like you to do is stop and think for a minute, what is the other angle inside that right angle? Stop the tape and decide what the other angle measures. Since the 2 angles form a right angle, and a right angle is 90 degrees, that means that the other angle must be 90 minus 39 degrees, which I believe would be 51 degrees. These angles are called complementary. Okay? Now notice the complementary is not spelled like complimentary when you tell somebody what a wonderful dinner they made or what a lovely pair of shoes they bought. This is complement, and it means the angle that is 90 degrees minus the given angle. That is, 2 angles that form a right angle are called complementary angles. Here's another picture. This is a straight angle, 180 degrees, and we're told that one of the angles is 75 degrees. I want you to stop the tape and decide what the missing angle is. Since the 2 angles formed a straight angle, that is, their sum is 180 degrees, the missing angle must measure 105 degrees. Two angles that form a straight angle, that is, two angles whose sum is 180 degrees, are called supplementary. So you'll notice there's quite a bit of jargon, a lot of vocabulary in geometry, but again, it's very specific. We never confuse complementary angles with supplementary angles. One of the more basic shapes in geometry, a shape we see regularly every day, is a quadrilateral. Now, you say, wait a second, I thought they was called polygons. Yes, you're right, and I believe, and I'm no linguist, I really can't verify this is true, but I've been told by many people, and therefore I believe, that the gon is from the Greek and lateral is from the Latin. So a quadrilateral means a four-sided figure. Probably it should be called a tetragon to be consistent with a polygon, but it's not. It's called a quadrilateral. And here we see three very basic types of quadrilaterals. The first is a quadrilateral, which is just a general four-sided polygon. We remember what a polygon is, and now we just say whatever a polygon was, which was, of course, has line segments with sides that meet at the endpoints to form angles, and it's closed. This would be a polygon with four sides. If those four sides are all the same, if they're all equal, and the four angles are all the same, meaning they're right angles, we have what's called a square. And notice we've marked up the angles and the sides to show that all four sides are the same, little tick marks indicating that, and the angles are all the same. In fact, they're right angles. A shape that has four sides that are all the same, whose angles are not all the same, is called a rhombus. So simply saying that a square is a quadrilateral with four equal sides is incorrect. It is not. It's a rhombus. A square is a quadrilateral with four equal sides and four equal angles, or four right angles. Three other very common types of quadrilaterals, are shown next. A rectangle, probably the most common quadrilateral shape, is a quadrilateral with opposite sides equal. So notice that the left and right sides have a little one tick mark. The top and bottom have two tick marks. The tick marks indicating equal lengths. So the top and bottom are equal. The left and right sides are equal to each other, but not necessarily equal to the top and bottom. And all four angles are right angles. A question is sometimes asked, is a square a rectangle? And many of my students say no. Well, they're wrong, because a square is a rectangle. A square has all the parts that a rectangle has to have. It has opposite sides equal. It has four right angles. It is a quadrilateral. A square is simply a rectangle where all the sides are the same, not just opposite sides. Is a rectangle a square? Well, it might be, but in general, most rectangles are not squares. Now, what if we had a rectangle, except the angles weren't all the same? They weren't all right angles. Well, that's called a parallelogram. And the opposite sides are equal, like a rectangle, but the angles are not all the same. They're not all right angles. In fact, the opposite sides in a parallelogram and a rectangle and a square and a rhombus are all parallel. So a rhombus and a square and a rectangle are more specific forms of parallelograms. A trapezoid has only one pair of sides that are parallel. And you'll notice we've marked the top and bottom of this trapezoid with a little thing that looks like a greater than symbol, and that simply shows that those two line segments are parallel. So that's a trapezoid. Now, in learning about quadrilaterals and other shapes, one of the things we're concerned about is area. And what we're going to discuss now is what area is. What I'd like you to do is stop the tape and think about what area measures. It may be not quite as easy as you think. Come back when you have a definition of what area measures. Area measures the surface of a two-dimensional shape. And when you've heard that, you say, oh yeah, that makes sense, but it's very difficult for many people to tell us what area is. They can tell us how to find area, what we find the area of, but the idea that area measures surface is not one that's quite obvious to many people. Hopefully now it's obvious to you. What do we measure the area of? Well, we can measure the area of a floor if we're buying carpet or tiles, floor tiles. We can measure the area of a wall or a set of walls to paint them. For example, when you buy most paint, it may say that a gallon of paint equals so many square feet. In fact, most area is measured in square something, square meters, square miles, square feet. There are two measurements that don't have the word square. There's an acre, which is a measurement used for land, and a hectare, which is also used, that's in the metric system. We'll talk about the metric system in a lesson coming up in a few more hours of tape. But basically, area measures surface. And the basic unit of area is a square. Now, I'm not the world's greatest square drawer, but let's assume this is a square. And if that square was 1 foot on a side, every side was 1 foot, that would be called a square foot. The question now is, how do we measure area? Well, the answer is, we're going to find out how many squares fit inside a figure. And if each of those squares is 1 square inch, the area is in square inches. If the measurement of the square, the unit square, is 1 square meter, then we're going to measure the area in square meters. If we're measuring something rather large and the basic unit square is a square mile, then the measurement will be in square miles. So let me erase this and take a look at a larger square. And here is a square, and let's assume that this square is 3 meters on a side. Each of the sides are the same, they're all 3 meters. How many 1 square meter squares can I divide that square into? Well, let's see. I could certainly have, and again, I know those lines aren't very straight, but that's okay. You can imagine them being straight. I'm not paid to be an artist here. We can imagine those are 3 columns of squares, each 1 meter across. And of course, in each column we have 3 squares. Now, each of those squares is 1 square meter, 1 meter on a side. How many 1 square meter squares are there in that big square? There appear to be 9. Do you see how we got the 9 without counting squares? Well, you can say, oh, sure, because there's 3 rows and 3 columns. 3 times 3 is 9. And in fact, as I believe we mentioned earlier, we talk about a power. Something to the second power is called the square. And the reason is that the area of a square is the side times itself, or the side to the second power, or the side squared. And that is the general formula for the area of a square. Now we want to look at the area of a rectangle. So let me erase this. And let's draw a rectangle up here. Not too big. How about a rectangle that was, let's say 4 inches by 2 inches. And there are squares. Each of those squares is 1 square inch. We have 4 squares in each row. We have 2 rows. 2 times 4, or 4 times 2, is 8 square inches. Okay? How do we do that without counting squares? Could you imagine if this rectangle was 17 by 35? Do you want to draw all those squares? I certainly don't. What we can see is that the number of squares will be the length times the width, and therefore the area of a rectangle is the length times the width. This is consistent, by the way, with the area of a square. Remember, earlier we said that a square is a rectangle, where all the sides are the same. In a square, the length is side S, the width is side S, and therefore S times S for a square really is the length times the width. So the area of a rectangle is the length times the width. But not everything is rectangles. One of the other important shapes for which we need to find the area, and this will be helpful later on in lesson 20, is the area of a parallelogram. Here's a parallelogram. Okay, we have a length, and we don't talk about a width, we really have the height, which is the distance between the top and the bottom. Now, sometimes this length is called a base. I'll put a B in here, and the reason is that is to differentiate it from the length and the width of a rectangle. Now, what you do, imagine we then took this triangle, this right triangle over here at the extreme left side, cut it out, and pasted it right here. What shape would we have? We'd have a rectangle. And the height of the rectangle, or the width, would be h, and the length would be the same distance, b, the base. And therefore, the area of a parallelogram is the base times the height. Okay. Now, we're going to use this to find the area of a triangle, but that's going to be in lesson 20. Okay? Now, of course, we could do various numerical problems with this, but the idea is once you have the formula, the area of a square, side times itself, the area of a rectangle, length times width, the area of a parallelogram, base times height, just put the numbers in, multiply. Be sure both numbers have the same measurement. You can't multiply inches times feet. You change the feet to inches or the inches to feet because you want to have both measurements the same, and when you multiply, you get square inches, square feet, square meters. The area, when you're multiplying two distance measurements, length times width or base times height, will always be square something, square feet, square meters, square kilometers, whatever. Okay. There's also a measurement for three-dimensional objects, and that's called volume. The basic unit of area is a square. The basic unit of volume is a cube. And the question is asked, how many cubes of a unit size can we fit into a three-dimensional figure? Well, let's take a look at a cube. And again, please excuse my artwork. I barely passed art in high school. That's a long story. Here's a cube. And let's say this cube is 3 centimeters on a side. That is, it's 3 centimeters wide, 3 centimeters high, and 3 centimeters deep. Okay? Let's just say that S equals 3 centimeters, the side. Well, we could have 3 packs of 1 cubic inch cubes there, and 3 here, and of course 3 here. And what you could see is we're going to have how many cubes? Well, we're going to have 3 columns, if you will, each stacked with 1, 2, 3, 4, 5, 6, 7, 8, 9 cubes, or 3 times 9, which is 27. That is, the volume of a cube is going to be its side times its side times its side to the third power, which is, as we said earlier, why the third power is called the cube. So, the volume of a cube is the side to the third power. If this cube had a side of 8 miles, we'd have 8 times 8 times 8, which is 512 cubic miles. And of course, in many cases, if your house is heated with natural gas, you buy that gas by the cubic feet. How they measure it, I don't know, because I've never seen a cube of gas. But that's for another interesting science experiment, I guess. The one last thing I want to talk about is a very common shape we call a box, but the official mathematical name is a rectangular solid or rectangular prism. And we'll talk about prisms in lesson 20. So here's this box. The box has a length and a height and a depth. Well, I think you could see that if this length was 4 and the height was 3 and the depth was 2, that basically we would measure and we'd have 4 times 3 cubes in the front and we'd have 2 racks of those 12 cubes. Or we'd have 3 times 4 times 2, 24 cubes of unit size. And therefore, the volume of a rectangular prism or a box is the length times the height times the depth. Okay, we've looked at some very basic geometric terms. We've looked at some very basic geometric shapes. We've also talked about polygons as many-sided figures. We've looked at a very specific polygon, the quadrilateral, the 4-sided figure, the square, the rectangle, the rhombus, and the parallelogram, and the trapezoid, all of which are 4-sided quadrilaterals. We've looked at area, which is a measurement of surface, and we've seen that the area of a square is side times itself, side squared. The area of a rectangle is length times width, and the area of a parallelogram is base times height. We've also looked at volume, a 3-dimensional measurement of space, and we've seen that the basic unit is cube, and that we measure the volume of a cube by taking the side and raising it to the third power, cubing the side. and that the volume of a box or rectangular prism or rectangular solid, three different names for the same shape, is the length times the height times the depth. We'll continue our discussion of geometry in Lesson 20.